I'm Greg Burns, and I study biomechanics, so mostly locomotion, but some other stuff too. And so, this is the sort of stuff I'm interested in. This is what we do in my lab. I'm really interested in movement. I'm interested mostly with animals, to be honest, but I've done some work on people as well. But we're really interested in basically, how animals deal with their environment, much like these great people American Indian Warrior. And so just real fast, I'm going to tell you about a few things that I've done and that I've been working on and things. So for my PhD, I studied gliding, and I'll talk more about that at the end, but I'm sort of doing more gliding stuff now. But I had some students that have been interested in human running, so we've done some work on human running. So a couple years ago, we started a project looking at humans running over rough terrain. Does anybody have any idea what happens when you run over rough terrain? What's your body look like? Any ideas? Never run or bump stuff. So it turns out what you do, normally you run like this. When you hit bumpy terrain, you do this. So you run like a duck. That's what we found. So basically what happens, the shoulders, the elbows come up, and instead of running sort of like this, you're running more like this. And we think that's helping balance, things like that. But I'm not going to cover much of that, but we've done some running stuff, so I'm pretty open to lots of different things. I've also done lots of work on squirrels. So I'm interested in how squirrels jump, how they deal with small branches, how they jump off of squishy, bendy branches, things like that. And so it turns out actually the BBC came last year and filmed some stuff in my lab. There's a squirrel documentary that's supposed to come out at some point here. You can watch me be embarrassed on TV on squirrels. It wasn't bad. I thought it was going to be that's all. It's not too embarrassing, but it's a little embarrassing. I've also studied snakes. So for my postdoc, I did lots of snakes, and I'd like to do some more snake stuff in the reasonably near future. I'm not talking too much about today, but what we're going to talk about is stuff with gliding mammals that I've really sort of picked back up again. And so what we're really going to talk about is sort of how gliding animals control their membrane, right, the skin between their arms and legs, and what that has to do with the forces associated with gliding. All right. So this is an animal called a flugo. So it's big. It's actually about this big. And so for some things, it turns out a big animal is really nice to study these kind of things. If you look really closely, I guess I actually could just put that's all. Right, so that's actually a baby. So this thing's flying in the air, and the baby's like clinging to the mother's belly right there, right? So it's going to land, very softly. This baby's going to be happy and all right. And so think about gliding, right? Everyone's thrown a paper airplane before. Who's thrown a paper airplane? Anyone know? All right, so basically a paper airplane, right? There's lift, there's drag, and all those forces balance out, and so it's really simple. It turns out gliding actually isn't that simple. We're learning as we study lots of gliding things. So I study gliding mammals, we will study lizards, snakes, frogs, all sorts of things glide. It turns out basically everything is thrown out of a tree glides. Don't go throw your pets out of trees, but in general, lots of things glide. It's really actually pretty complicated. Okay, so what's happening is the forces are always changing, right, which makes it hard, unfortunately. It turns out that the shape of the animal is always changing. Again, it makes it really, really hard. And so we're just starting to sort of scratch the surface on how this actually works. And so what we've learned is that having flexible membranes makes flying better in some ways, but it also makes it sort of more complex to actually understand what's happening. And so I actually bring in lots of colleagues from lots of different fields. So I work with people, they're engineers and most things like that to help with some of the things that I don't have the expertise to do. What's really cool about flexible membranes is that they actually can enhance aerodynamic performance. Right? So if I had a paper airplane or even a 747 where I'm flying across the ocean, it turns out the aerodynamics are pretty well understood. And we're, like I said, we're just getting at sort of how the aerodynamics of flexible membranes work. But what we do know is that they can produce greater forces, especially at higher angle of attack, right? So if you're flying level, like an airplane, right, your wings only tip up a little bit. Lots of these gliding animals will actually fly with a membrane sort of that's very tipped up. And so these things can generate lots of force at high angle of attack. It turns out they can also produce, and so what happens in an airplane, has there ever been an airplane, does anyone do any stunt flying or anything like that? Dr. Tell's not here, so he can't tell us about doing loops and stuff. But basically what happens if you're a regular airplane and your wing tips up too far, basically you don't produce any more upward force and the plane falls to the sky and it's bad. The reason airplanes do that is because they have such a giant engine that it pushes them so fast that it never actually happens. But if it did happen, you would fall off sky quickly. Turns out in gliding mammals and other gliding things, you can actually tip that membrane up much, much higher and still produce lots of force. So they actually operate at a much higher angle of attack. And so we know, like I said, it's the very minimum really about how these flexible membranes work. All right, but they're really impressive. Okay, so here's going to be a video of an animal. The animal I think is right in here somewhere. And so what I want you to do is I want you to watch this membrane. As it takes off, you're going to see the membrane bounce around. It's going to sort of squeeze in. It's going to open out. It's going to do all sorts of stuff. And just look at how much control this animal actually has over his gliding membrane. And so there's the guy with the net trying to harass it there, right? Here's the guy. So watch the membrane. It's going to kind of bounce a few times. See his tail go up and down, right? Eventually, it's going to go through some narrow spot. It's going to bring his arms in. So there, see it brings his arms in like this, and it actually spreads back out. And then the guy tries to get down here with the net. Doesn't have good luck. Which is probably good. But it turns out they have exquisite control over what they're doing, right? So you sort of think, oh, it's like a paper airplane, just glass here, there. Turns out all these animals, this is a clue by the flying squirrel, it turns out gliding snakes, gliding frogs, not quite so good, but gliding lizards really, really good. They all have this really exquisite control. So they must have lots of sort of knobs that you can turn right to actually control flight. Okay. And so that's another thing we're interested in is basically how are they controlling shape and therefore the forces. And so the way they can change shape is they can move their limbs, right? We saw them move their limbs in, saw them move their limbs out, their tails were flat around, stuff like that. It turns out in the membrane there's lots of little muscles, and I'll show you that in a minute. And so they need to basically actively contract these muscles and make the membrane either tighter or looser, sort of like a parachute. And also the actual properties, the properties of the skin itself can affect how the wing forms. Right? And so this is pretty cool because these animals right here, the flying squirrel down here, flew up there on a tree, right? You don't see the membrane, right? This animal can run around, it looks like just a squirrel or like sort of weird bat-like creature, right? It turns out they go from like that to this. And they can go run in the trees and they also fly. Right? So what is it that allows them to have this amazing shape change? Right? So this is one of the things we're really interested in. We started doing some morphology, and I'll show you a little bit about that. So these belugas actually live in Southeast Asia. It's really a bummer because I have to go to Southeast Asia. It's terrible. But basically, this is a beluga, right? And so what we're going to do is we're going to look at some areas of the wing. What you see here is actually a pretty big muscle there. But it turns out you'll see all along here there's lots of little muscles. All along here there's lots of little muscles. Back here there's lots of muscles. Right? And so people sort of hypothesize that these muscles were there. Okay, so we look here at these different regions, right? I don't know if you can see those tiny little white stripes. Each of those little stripes, that's actually a tiny little muscle. Tiny little muscle, right? That's maybe 5, 6, 10 fibers thick. Up in the front edge of the wing up here, there's lots of muscles running that way. There's also some facial ones running that way too that you can only see here. And then along the edge of the wing, there's lots of them that are running this way. And so, like I said, people even 100 years ago said, oh, there's probably some muscles in there, but they just couldn't actually see them. So we were actually the first people to actually be able to describe these muscles in some detail, which is pretty neat. And so what it says is if you have all these little muscles, right, basically you can do lots of things in the membrane. Okay? And you end up with behavior that looks like this. Right here again is beluga. This is a video my friend took. Basically be in slow motion, and then you'll see it fast motion. But again, you see all this movement of the membrane, right? The limbs are moving a little bit, the tail is flapping. Lots of things are happening. All right. There's real time. So they actually fly pretty fast. Turns out it's hard to chase them, right? They glide at night in the forest, and you're like, oh, where'd it go? So it's pretty hard. But in the lab, we have some tricks we can do. And so what we're sort of actively doing now, my students and I, is we're trying to understand the shape of the membrane during flight. Okay? And so, who likes to play video games? Anyone have an Xbox? Yes, you like neck thing, right? They like dance in front of them and stuff. It follows you. It turns out flying squirrels also like to dance in front of the Kinect. And there's actually so they don't make the Kinect anymore, but Intel actually makes sort of a new camera that does something similar but it films faster. And basically what it does is it gives us a 3D representation of the scene that's filmed. Okay? And the way it works is that there's some basic image sensors, basic cameras. It actually projects an infrared pattern onto the scene, so lots of little dots. And basically what it can do is it has these two cameras. You can register the view from the two cameras so it knows how powerful those two cameras are, and it can basically give you a three-dimensional scene. All right, so this sort of looks like, this is the connector, this is for the other system, right? So you see all these little white dots, those are actually projected from the IR camera. This is just a picture of somebody. And this is basically the depth image again. So you get this 3D image. And so what we can do is we can use it to actually figure out what the shape is of these animals as they run. Okay? And it has pretty good resolution. It's not great, but it's pretty good. And so I did this. And so anyone's been in my lab may have seen the giant blue tarp in my lab. This sort of house. So that's the blue tarp. Turns out I set up some little fake trees in there, and here's a flying squirrel jumping between two things. And what we can do is we can basically pull that squirrel out, make it a point cloud so we sort of know its shape, and we can basically fit a surface to it to look to see what the shape of the building is. All right. So there we pull out the squirrel. And we do that when the animal's flying. We can also, if we have a carcass, we can actually use it to like basically make a model. This is actually glue that's not flying. Basically what we do is we can pull out this image of a glue mill, right? So this is actually suspended. So we can take a more detailed image. And what we do is we can fit a surface to it so it has this nice smooth wing surface, right? So there's one limb, there's the other limb. This is actually the bottom surface, so that's like the belly. This head's right there, which you can sort of see the shape right there. And so what we do is we can actually then try and run some aerodynamic simulation on this, which I'll talk about in a second. We can also look at how the shape changes as the animal glides throughout the glide. Okay? And so what we do is we can take these point clouds, and we basically make slices for them. Okay, so here's my flying squirrel down here. All right, so basically what you can do is you can slice it this way, right, and look at the shape of the membrane. You can slice it that way and look at the shape of the membrane. And so what we see is that this is the span-wise, so these are the red lines here. And in the front, it's pretty flat. As you sort of get towards the middle, it starts to be more curved side to side. In the back end, it's kind of flat. And from the sort of front of the animal to the back of the animal, you can see, right, the head's a little bit lower, and you start to get some curves sort of towards the middle of the animal. And then one side, it's actually asymmetrical in this case. And so what we do is we can compare what the shape looks like in different parts of the glide and see, this is just the first step, does shape change? Right? So as the animal takes off, and as the animal lands, how does shape change? All right? And so we've gotten that far. We haven't gotten too much farther than that yet. What we know is that there's big changes, especially early on. These are for very short glides, like 2.5 meters. So this is a very long glide. But so at first, there's a big curve sort of left to right. So the animal starts out like this. All right? And as it goes farther, it flattens up, like straight lift up like that. Okay. And chord-wise, it's pretty flat to start with. It becomes more and more curved as it glides farther. Okay, so we see these two changes. And what this really tells us is that we can use this method to sort of understand how shapes change. Okay. But we have another set of tools that may turn out to be more useful. And so if we can actually take good images of these animals, what we do is we can actually take the shape, and there's lots and lots of sort of mathematical models of aerodynamics of various membranes and things like this. And so we can actually plug in our shape into a mathematical model and basically get what the trajectory should look like if it jumps this high at this angle like this. So this is an example that the colleague of mine did. And so basically this blue line here is basically the trajectory. What the red lines are, that's the velocity, so it takes off and leaps in some direction that way. The velocity sort of starts heading down, actually velocity is pointing down a little while, points back out. And the green is actually the orientation of the body, so the body's pretty much along the flight path until the very end, and it pitches up before it lands, and it changes the velocity vector and lands soft. Okay, this just shows the pitch angle and the angle of attack, so how much is it altered from basically its direction of movement. And this one here, you don't need to worry about this, but this one basically shows the position and velocities in each of the directions. And so, you might wonder, why do we care about this? Right? Do we care? Maybe not. Turns out we can do cool stuff. We can make robots. Okay, so this is actually my colleague. This is Matthew. He's at the Max Planck Institute in Germany. And he's the one that did the mathematical modeling. And it turns out we started making robots together. This is actually a robot that he built before. We built this really cool robot that can do this. So basically, this robot's going to jump into something. Oh, what happened? I crashed, so that's not good. All right, let me try that one more time. See if we can get this to work. I won't make it this time. Now, basically, the robot's down here. It's going to jump up in the air. So see it jumping? Oh, it's anyway. All right, hold on. do is you can look at it. I'm having all sorts of trouble here. I just check this. We'll stop here, and I will show you the moves separately. All right, you see everything there. All right, so basically, another. So here's the here's the video. We'll show this one first. All right, so this is robotics. I'll play again once it stops. All right, so the robot's down here. It's going to jump up in the air. Here's going to jump over him for a minute. All right, basically, just based on inertia, it's going to change shape. Basically, come into a basic glide configuration, right? So its wings are going to separate, spread out, and it's going to glide. And what we've been working on is basically making it's not actually a very good glider. It's a good jumper, it's not a very good glider. So we're trying to make it a better glider. Right? So its wings are spread out now, and it's sort of gliding over him. Pretty cool, right? Yeah. So I was in Germany over the summer, actually working with this guy trying to make this robot better. Not sure how much help I did, but made it a little better. All right, well, so the last part is, I won't show the movie, but basically what you would have seen, but the movie work, is that basically it's a picture of a Kalugo gliding. And so in Singapore, we just got some money to do a conservation project. So in one place in Singapore, they're widening the road, basically where these animals are living. And so they put up some sort of fake trees to help animals cross the road. And so just yesterday, actually, my friend sent me a little cell phone video as he was driving down this road of a Kalugo using one of these new trees that got put in. It's the first evidence that any of these animals are actually using these trees. And so basically what we're trying to do is we're trying to basically see, does this new road affect the connectivity of the forest on either side of the road? At least from this first little bit of evidence, it suggests that maybe they don't. But we're actually putting GPS collars on animals. We're setting up a radar system to track animals as they cross the road. So it'll be pretty cool once everything gets done. So basically, you can do lots of cool things with biomechanics. You can do conservation, you can do ecology, you can do robotics, you can do lots and lots of stuff. So it's not just me fooling around most of the time. All right, and so that's the end of it. I just want to thank you guys for your attention and thank people that give me money and things like that. Questions, please let me know. Any questions? All right, Bueller.
Friday. We have 10 minutes left of this. We'll try to make this as painless as possible. And hopefully try to make this as interesting as possible. So, number one, I just want to say my colleagues do some amazing work. We got Leave Our Ants, we got Kalugos that Glide, we got lights. So, really nice, beautiful, awesome stuff. So I study skeletons, which admittedly is not as cool. Right? So we don't have these really cool things to do like leaves and grow fungus, but there are some really neat aspects of it. So let me just tell you a little bit about what I do. I'm going to try to make this quick. So I'm a developmental biologist. And we talked about colony development, so I'm kind of the old school developmental guy. So I'm like interested in how you go from a single cell fertilized egg to that. Right, and so needless to say, that's a pretty complex process. There's a lot of stuff that has to go on. And I've always found this to be absolutely fascinating. The fact that that will turn into that with basically just your genes being expressed. And so, shockingly, there's only a couple processes that really are involved in this. And so, obviously, cell growth, division, single cell thing, the multicellular guy here. And so, that's pretty obvious. Cell fate determination. So, cells have to decide what they are, right? So, there's a lot of signaling that happens in here as the cells try to pick what team they're going to play for. There's cellular differentiation. That's when cells actually start to become what they're supposed to become. So, once you know you're a liver cell, you start actually becoming a liver cell. This one is the one I'm most interested in, morphogenesis. So this is the process where you actually build stuff. So when you build organs, when you build limbs, when you build your face during development, those are all morphogenetic factors, right? So you decided which grown, you decided what you could eat, you differentiate, and then you actually build your organs and structure. This is what I'm most interested in. All right, so I don't study this. I have 4 of these. Study this guy. And again, admittedly pretty boring, right? So this is C. elegans. It's a nematode. They just eat bacteria. They just live in like out in gardens and stuff. They're not very exciting. They're not parasites. They don't co-evolve probably with anything. So this is their life cycle. So there's hermaphrodites and there's males. Hermaphrodites essentially a female. She just makes a little sperm. And then they go through these larval stages. And what I study is actually this larva, how it can either develop into a hermaphrodite or develop into a male. Right, so I study how you basically create this sex difference between males and hermaphrodites. So specifically, I focus on the tail. And so the hermaphrodite tail is pointy, and the male tail is not. It's one-ended and has a bunch of stuff hanging off of it that it basically uses to touch receptors and sensitive body. Right, so I study a morphogenetic process that basically takes a tail of a larval male, looks like that, to make it into that. That happens over the course of just a couple hours. You can actually watch this happen with a microscope. So I'm going to show you some images. So this is the tail of a male, and it's made up of exactly 4 cells. These cells, first thing they do to start becoming that is they fuse together. So all of the 4 cells fuse together to make one big cell with multiple nuclei inside it. They then pull themselves off. So this is the cuticle of the larva. They pull themselves off the cuticle and they start migrating forward. We call this tail fin retraction. They're migrating in this direction. This is then followed by a separate retraction event where the whole tail now starts migrating forward. And these are actually those little mechanosensory neurons called rays. And then you end up with this structure. Right, so all that is very specific. So if you look in hermaphrodite, none of that stuff happens. You end up with just this pointy tail on it. So that's what I study. I study this. And I study how that works. And I study the genes of it. So the obvious question is that. And so this is the question my parents always ask me. They're like, we paid for college and you study what? Right? So it's a really weird thing to study, admittedly. So I spend a lot of my life thinking about how that works. Right? So the obvious question is, who cares about how that works? So hopefully, probably not, but hopefully you'll understand why I study this, study into this. You'll care at least a little bit. Right? So why do you care? First of all, I think it's a great model for morphogenesis. How we build structures in development. And so I'm going to show you one little video of morphogenesis. What this is not C. elegans. This is from a zebrafish. And what it's going to do is we're going to build an eye out of this collection of stuff. And so what you're looking at right here, that's actually part of the brain. It's a little outpocket on the brain. And this is the tissue that lies over it. And over the course of a couple hours, this fish is going to build itself an eye by morphogenesis. And so what we've actually done is we've labeled the outsides of the cell with green. There's a nuclei there. And so what you're going to see, all of a sudden, you're going to see an eye pop out of nowhere. Right, so cells start moving around. You can kind of see them kind of shifting, moving, migrating. Some are still attached to one another. Some aren't attached to each other. And all of a sudden, you start to see this little pump form. That's the retina. And all of a sudden, right in here, you're going to see a lens form. It's going to like, cells are going to change their shape. They're going to come together. They're going to bind. The retina is now starting to form. There's actually 2 layers of the retina, and there's the lens. That's morphogenesis. Right, so you take just kind of a lot of cells, and all of a sudden they build a structure over the course of a couple hours. There are tons of questions about how that works. It's obviously really complex. And actually, we know very, very little about that. So this is a very complex process. I'm actually studying a similar process, but I'm only using 4 cells instead of hundreds of cells that are involved in the process. So the idea is I can study male-tail morphogenesis, and that will tell us about morphogenesis in general. All right. The other aspect of my project that I think is really interesting, it can tell us how sex differences evolve or form or develop. So almost all animals are sexually dimorphic. So males and females are different. Right? And some are really big and obvious, like these stalk-eyed flies. Drosophila, which is pretty subtle. There's some subtle differences. We're fairly subtle. We have little dinosaurs. Et cetera, et cetera. So we can study sex-specific development, which is actually kind of an interesting question if you think about it, right? So we essentially have 2 organisms which are almost genetically identical, which is the difference in our sex chromosomes. And you can take all of these processes, but the sex of the organism has to then talk to all these processes to make sexually dimorphic animals. So I'm interested in how this works. The last thing that I think my project will tell us about is how cancer cells metastasize. It's like a last term, right? Like, what the hell? Right? So cancer cell metastasis. So you got a primary tumor here. These usually will kill you in cancer is it'll get into your bloodstream and you'll find second sites and make second tumors. Intracellular metastasis, what happens is you have a primary tumor, these cells become invasive. They actually make little projections called invatopodia off their cells. They will migrate through, they'll change attachments, and they'll migrate into our bloodstream, and then they'll migrate through other cells and get into a second cell. Right? So they make these really cool things, these invatopodia. That's a projection off the cell. And it's made up of actin microfilaments. So there are tons of actin microfilaments in this guy, and this allows it to invade. The invasiveness is really, really bad. And so I think this process, when we're tracking our tail, is an invasion. Right? So this is actually showing you, it's shown very well. That's the actin cytoskeleton, or at least the tail tip cell. And so that is a bunch of actin forming right at the front edge of that actin. And it's invading, and it ends up migrating to a lot there. And so it's a really simple little example of cell migration. And I think you could probably use similar mechanisms if cancer cells used to metastasize. Does that make sense? Okay, good. All right, so I got 3 minutes. I'm going to tell you a very little bit about what I do. And so if I'm going to study this process, what I'm interested in is the genes. The genes that come on in here and make this happen. All right, so I'm going to totally simplify what I do, and we're just going to show you this. And so one thing that we can do is try to identify genes that are involved in this process. I can take a male. So this male right here, the box who basically undergo this morphogenesis. This is a hermaphrodite. She does not undergo this morphogenesis. A couple years ago, I went down to my collaborators at NYU, and we basically took a little laser and cut off the tail tips. A ton of males, a ton of hermaphrodites. And we took all the messenger RNAs, so those are all the genes that are expressed in those cells. And we basically did RNA sequencing. So we sequenced all the messenger RNAs, and that'll tell us all the genes that are expressed in the male tail and all the genes that are expressed in the female tail. So in the next minute and a half, I'm going to tell you about 2 of these genes. A gene called GND3, a gene called CDH7. There's about 1,000 or so genes here. We study about 70 of them. So I'm simplifying, I'm telling you 2. Right, so DMD3, real quick. Okay, let me just show you this really fast. One of the things we want to be able to do is identify where genes are expressed in C. elegans, and so this is how we do it. So every gene has a coding sequence that kind of makes the protein, right? That makes the protein that's going to give me the regulatory sequence that controls when and where it's expressed. And so to understand where some gene is expressed, in this case we're looking at the MD3s, we take off the coding sequence, and we add the coding sequence of this guy. This is green fluorescent protein. It comes from a jellyfish, and it makes a little fluorophore. So this fluorophore, when you hit it with makes a protein, and when you hit it with ultraviolet lights, it basically fluoresces. And so I take that and I hook it up to my regulatory region, and then I take that and I inject it into worms. So I make this piece of DNA in the lab. We take a little needle and we inject it into worms. This gets into them. That's awesome animation. Appreciate that. And this will get put into their eggs. And then they actually put it into their nucleus, and they will express it like it was their own, and you make a whole bunch of transgenic worms. So these are transgenics. They're carrying this piece of DNA that I made in the lab, and they're carrying along inside the gene. And then what I can do is I can look at these guys and see what pattern of fluorescence I get. Does that make sense? At least at some level? And so I get stuff that looks like this. And so this is my favorite picture of all time. This is the MD3. This is the expression pattern, and it's expressed highly in the tail tip. We thought it might be, and it's not in the hermaphrodites. Now, not. Make sense? Basically we're showing the expression. Okay. We also know if I screw up the MD3 gene, it's actually necessary for this process. And so here's a normal male, they do this, the MD3 doesn't do this properly, and you end up with this pointy little tail tip because the male doesn't control the genesis properly. Okay, fine. So it's beautifully expressed, it shows this nice. And so the obvious question is, who the hell cares about the MD3? What is the MD3? What does it do? What's cool about the MD3 is that we have multiple versions of DMD3 in our genome. And so we have like 11 DMD3-like genes in our genome, including 3 right here on the very tip of chromosome 9. It turns out, if you chop off the tip of chromosome 9, so this is our chromosome, human chromosome, there are 3 DMD3-like genes in there. It's a gene called DMRT1, DMRT2, and DMRT3. You take that tip off the chromosome, your XY, you develop as a female. Right? So these 3 genes, you have to have them to develop as males. We do. Right? And so what that tells us is that by studying DMD3, which is this gene that's necessary for males to develop as elegans, that tells us a little bit about how basically sex talks to development. Right? So DMD3 is one of these core fundamental regulators of how sex controls development. Okay? Got it. time's up. I have a really cool story. I told you. So I've been studying DMD3 for a really, really long time. I've been studying this for 15 years, 13 years, long time. I've been studying this other gene for 4 weeks, but I'm really excited about it. Gene called CD87. So I did the same experiment. I hooked up the regulatory region of this gene CD87, and I see this patch. Right? So this is one of these things identified by RNA sequencing, and it's expressed in the tail fin of the male as a contracting, not expressed. Right? So you obviously are thinking right now, why am I thinking this? Well, the other question you might ask is, what the heck is CD87? CD87 is a gene called, it codes for a protein called cadherin. What cadherins do is they control cell-cell junctions. So this is one cell, that's an A ring cell. These cadherins are basically transmembrane domain proteins. They stick up in the plasma membrane and they attach adjacent cells to them. Right? So really important stuff. And they're highly conserved. And so we actually have tons of cadherins in our genome that basically make all these different proteins that help our cells attach to one another. CD87 is similar to this really poorly named cadherin in us called FAT4. Right? So actually tell you later why it's called FAT4. But this is basically showing you CD87's amino acid sequence, and this is FAT4, our FAT4 amino acid sequence, and they're the same.